What you see here on the screen behind me is a snapshot of a little village along the coast of South India. This is where I grew up, and this is where, as an 11-year-old, I saw this exact coast being washed off by the waves of tsunami. It was very hard, it hit very close. As you can see, I did manage to escape, but it was almost a near miss. And I was already quite aware of global warming and climate change as a child, but when the waves of tsunami hit me, I was quite anxious. It's taking me a toll even now to look at this picture and talk to you again. But what I realized is that there is an imminent climate crisis is upon us, and the rising levels of sea scared me a lot as a child, especially as an 11-year-old. Ever since, scientists have been struggling to find a solution, a greener way of making electricity where there is possibly less or no emissions of CO2 in the atmosphere. It's a very grim start, but let's get to the reality. We all are quite aware of solar panels, and we see quite a lot of them. I would like to have a show of hands of how many of you have seen these solar panels. Amazing, everybody has seen a solar panel. As you can see, I agree with most of you, it is ugly. It is really ugly, it is bulky. Most Dutch roofs can't handle them of their weight. But they do in fact work. They absorb all the sunlight that hits on them and can convert them into a green source of electricity. But we also live in the Netherlands where sun does not like us for some reason, which leads to the biggest problem, as Sarah a little bit touched upon it. It's the intermittency of energy production, which involves finding an intermittent technology that can give us seamless power throughout the whole day. And this is where electrochemistry comes in. As the name suggests, electrochemistry is where you can use electricity to either drive a chemical reaction or do some chemical reactions to make green electricity. And electrochemistry, to me, is a very multifaceted technology. It can make electricity, it can store electricity in the form of batteries, but can also make green fuels from CO2 from the atmosphere into something like a syngas. Okay, we've all seen solar panels, but how does an electrochemical cell look like? We don't see it quite often. It's actually very simple, and you can actually make an electrochemical cell at home. This is a very simple example of how an electrochemical cell would look like. You can see what I have here is just a glass of water with a little bit of common salt, sodium chloride, the salt in it. And I've put 2 spoons in there right now. If you feel fancy, please use some forks. But please make sure that you don't use your antique forks because they will corrode. And what happens right now, if I apply a potential, I wish the video runs now. Yeah, so if you apply a potential, based on the potential and the polarity, you can start splitting water and making bubbles. And as you can see, if you swap the polarity, then the other metal will start doing the same thing. If it is this easy, okay, can we please go back to the previous one? Yes, if it is this easy, why are we not having an economy that is more hydrogen-based? The problem is that the metal that can do it very, very efficiently is platinum. And we all know that platinum is neither abundant nor cheap. And we cannot deploy a system into the economy which cannot be made so cheaply. And over the years, what electrochemists realized is that although the type of metal, in which case platinum, is very important, what is also very crucial is the liquid and the ions that is involved in the whole process. And this is exactly where my research comes into picture, where I use an atomic force microscope to probe these little nanometer layer of water that is interacting with the electrode. And I do this with this nice looking, very sharp tip. This tip essentially looks like a needle, and what I do is that I oscillate this and I get very close to this little interface of water and the metal. And when this tip gets closer to the surface, it sort of sticks, and what I do, especially in my experiments, is try to separate the contact of the tip from the interface. What I observe in my experiments is that based on what kind of iron you have in the solution, the tip sticks either very, very hard or not at all. And okay, cool, your tip sticks and not, but what is the implication? What I indirectly try to measure is something called interfacial energy. And the interfacial energy is very crucial because lower the interfacial energy, the easier it is for a chemical reaction to happen. So with this technique, you can literally figure out what combination of iron will work very well with the type of metal, potentially using even cheaper metals to find the lower interfacial energy possible so that you can drive a reaction at a much, much lower cost. And if we are able to achieve this, which I really hope we do, we would get to a point where we can use cheaper metals in combination with the right ions to make cheaper and easy deployable products. With this easy deployable products will come a day when people start using more sustainable energy, lowering emissions, and potentially, let's say, avoiding the climate crisis. As an 11-year-old, I had a lot of fear, but I also had a lot of hope. But what I would like is that we all act right now, really in an urgent way, that the current 11-year-old has just the hope and not the fear. Thank you.